Hello everyone. Today we will be building the stochastic alpha beta raw model, which is industry standard for interest rate derivatives. So, let's start by writing some basic import statements like import numpy as np, import matplotlib dot pyplot as plt, and from skippy dot optimize import minimize, and from skippy dot stats import norm, and import pandas as pd. So let's start. I have broken down this model into different steps. So let's start with the step one. So the problem is that the problem first is the volatility smiles in trusted market. So let me first define a function. Um, def show volatility smile problem. So what it demonstrated? It demonstrated the volatility smile pattern that black shows cannot explain. So let me switch on this. So why? And this is the fundamental market reality that motivated SABR development, and how it created empirical smile pattern using real market characteristics. So intuition, if volatility were constant, then all strikes should have the same implied volatility, which is not true in real market. So let's first of all let's do a step one. First, let's do a market setup. So we will define the forward rate and the strike range, and we need realistic interest rate market parameters to show the problem. So let's take f, it's the forward rate to 0.03, which is a 3% forward rate typically developed in developed market level. And let's take the strikes to be np dot space 0.02, 0.04, 15, which is 2 to 4%, and plus minus 33% moneyness. We are taking this. So and the step two, I will calculate the log moneyness. So what is that? So natural log of k upon f measures how far each strike is from the forward, which means why moneyness is the key variable that drives smile patterns. So the natural log transformation creates a symmetric scale. So intuition is that if log k upon f is equal to 0 at the money, and it's negative for in the money, and it's positive for out of the money. So let's create this. So it will be market volatility is equal to for k in strikes, moneyness is equal to np dot log f. So this is moneyness is equal to log n log natural log k upon f, which converts price ratios to symmetrical scale. So step 3 will be the empirical smile formula. So what is that? So it's the volatility k is equal to base volatility plus smile curvature plus skew of symmetry. So why are we using this? In real markets show quadratic curvatures plus linear skew. So quadratic term creates a smile and linear term creates a skew. So intuition is that far out of the money or in the money options have higher uncertainty. So let's take the base volatility to be 0.5, which is base volatility we are committed 25%, and the smile curvature is equal to 0.4. Smile curvature is equal to 0.4 by minus quadratic creates the smile shape. So we're using this, and the skew symmetry is equal to minus 0.15 moneyness. The linear creates the skew, which is negative is equal to in the money is greater than out of the money. So let's take the volatility, which is equal to base volatility plus smile curvature. I am again and again getting error here, and it will be skew asymmetry, and the market market volatility is band volatility. Okay, so let's go to step 4, the visualization part. So we'll plot market reality versus the Black-Scholes prediction, and we will visual comparison shows why Black-Scholes fail. So let me just copy paste that plotting part. So it's not that important for us to code. Just copy paste that part of code, and basically we will see the market reality interested options, and the problem is that interested volatility smiles. So in the next step, let's quantify the problem. So it will calculate the smile width and skew magnitude, and so the numbers make the problem concrete. So it will make the problem concrete. So let's see, the volatility range is equal to max of market volatilities, minimum of market is, and it will be in the money volatility is equal to market volatility deep, it will deep in the money, and out of the money volatility is equal to market which will be -3. Deep out of the money, the skew magnitude will come out to be absolute of in the money volatility minus out of the money volatility. So I'm copy pasting that code part also, which will show. Let me show the part. Let me run this, and basically I have an error. So let's see where the error is. This is this. Okay. So okay, I committed error here. So now it's working. So we can quantify problem. So market volatility range from 23.6 to 37.7%, and Black-Scholes prediction is constant 25%, and a smile width which is 14.1. It's a massive variation. So the skew magnitude 8.4% in the money versus out of money difference. The smile pattern show volatility is not constant. So but this graph tells us that smile curvature volatility is lowest at the money and higher away from money. Negative skew in the money options have higher volatility than out of the money. Fight to quality. Black-Scholes failure. Constant volatility assumptions completely goes wrong. And but this is tells us what is the need for the stochastic alpha beta rho model. We need a model that can create these patterns. So let's jump to the next step, in which I will give the stochastic volatility inside. So let me just print a statement like I have read. So this is a statement. So like here the sigma is sigma is constant, which is unrealistic, and the first inside the sigma should change, but how? So in SABR solution, both f and sigma are stochastic. So these are three core equations, which is the forward evolution, the stochastic volatility, and the correlation structure. The parameters are alpha is volume, volatility controls smile width. The CEV parameters control leverage effect, and beta controls CEV parameter, and the rho is correlation, it creates a skew asymmetry. And the sigma t is still now stochastic, not constant. We are copying it stochastic now. So let me just use a class parameters. So it will be like parameters. So finite self alpha is equal to 0.2 and beta is equal to 0.5, rho is equal to minus of 0.3, sigma naught is equal to 0.25. So let me just do the parameter validation. So I will this code here, the parameter validation code which I have written already. So for let's I am only writing the important parts of the code so that our time won't get wasted and explaining that part. Actually I have written this code already, and so just referring that part so that it's easier for both of us, easier for both of all of us. So that's the point. For beta is equal to beta and self dot rho, which is the correlation, and self dot sigma naught is equal to sigma naught, which is initial volatility. So let's just print and we'll initialize the interest rate derivatives parameters. So it will be something like this. So let's just see. Here is I have done an error. So I think so I did, oh sorry, error was here. So yeah, this is this. So I've set the parameters. So let's just build the Monte Carlo simulation. So let me write the function def simulate yard dynamics. So ask and n paths is equal to 2000 and n steps is which will take us 100. So the what I will tell you, like Monte Carlo simulation of the complete SABR stochastic system. Why before close from approximation we need to understand the SABR behavior. So discretize the continuous SDs using Euler scheme with correlated shocks. So this shows how f and sigma co-evolve with correlation rho. The mathematical foundation is the three core equations which we have discussed above, and I can also write so which is the Euler. Maybe also mention the mathematical foundation if someone wants to refer that part. Mention that. So this is the mathematical foundation. This is the Euler discretization. If anyone want to refer this, so let's start with step 1. So we will create a time discretization setup. So convert continuous time into discrete steps. So computers can't handle continuous time, need finite differences. So delta t is equal to t upon n steps gives us a time increment. Smaller delta t gives more accurate results, but it's more computationally expensive. So let's write this. dt is equal to t upon n steps. So the step 2 will be the memory allocation part. So let's pre-allocate arrays for the simulation paths, and why the efficient memory management for efficient memory for large simulations. So it will be f paths is equal to np dot zeros n paths n steps plus 1 sigma paths is equal to np dot zeros n paths and n steps plus 1, and the next step will be the initial condition. So set starting values of all paths. So all simulations start from current market state f0 f naught 0 is equal to f naught, sigma 0 is equal to sigma naught for all paths. So let's let's let the initial conditions, if we like them, f paths is equal to and sigma paths to mass dot sigma naught. So all paths start at same forward rate and all paths start at same volatility. So let's uh, let's write the main simulation loop. So it will be something like this. So for a step in range n steps. So the step the step 4a, we will generate correlated random shocks and we'll create Z1 Z2 with correlation rho using Cholesky decomposition, and the SABR requires correlated Brownian motion, not independent ones, and Z2 will be rho into Z1. So let me write that part so you will understand it how. So intuition is something like when rho is equal to negative 0.4, negative f shocks tend to get a positive sigma shocks. So let me write that equation only. Z1 is equal to np dot random dot normal size is equal to n paths, and Z2 is equal to mass dot rho Z1 plus np dot square root 1 minus mass dot rho 2 and np dot random dot normal size is equal to n paths. So let me explain the correlation creation one. So let me just, there's a several print statement. Let me just copy paste it for time utilization. So let me use this. So the step 4b is the current state value. So get ft and sigma t for the times this time step. So the SABR dynamics depend upon the current state value. So let us define it correctly. So it will be something like this, and f current is equal to f core paths step sigma current is equal to sigma paths step. So current volatilities, and the above part is the current forward rates, and this below part is the current volatilities. So let's apply the step 4c, where I will apply the SABR forward rate dynamics. So I will show you in the formula. This is a cos SABR forward rate evolution equation, and this will be, and we'll multiply current volatility into leverage factor into time scaling into random shock. So f to the power beta creates leverage effect. Higher rates can be more volatile. So let me use that, and will be df is equal to sigma current f current mass dot beta and np dot square root dt to z1. So let me also write a print statement for our easy explanation. It will be something like this. It will be for the understanding, explaining forward dynamics. So that. So, and let's get ahead to the step 4d. So we will applied the SABR volatility dynamics. So this make volatility itself stochastic. So this is a key SABR innovation. So volatility or volatility parameter into current volatility into time scaling into correlated shock. So already follow geometric boundary motions, always positive. So it will be like d sigma is equal to plus dot sigma dot alpha plus into sigma current into np dot square root dt into z2. Let me also print this. So the next 4e step we are coming will be the state update with positivity constraints. So interest rates and volatilities must remain positive, and using max function to enforce minimum values prevents mathematical artifacts from negative values. So we'll be using that. So it will be something like this. Step +1 p dot maximum current plus df. So f is greater than or equal to 0.1%, and sigma paths, the step +1 is equal to np dot maximum sigma current plus d sigma sigma will get then equal to 1%. So let me also update this clean state update once. So it will be something like this, and let's send the simulation part. So let's take the f0 to be 3% and t to be 1 year, and let's simulate that part, and let's also visualize the behavior. So the visualization code I will be just copying from my code which I have already written, so easy for everyone and no one's time get much of wasted. So something like this, and I'm writing the code of the plot one, which will show the forward rate path and show how f evolves under SABR dynamics and demonstrate stochastic volatility effects on forward rates. So this code is something like this, and the plot 2 which I will be making will be the show the volatility paths, show how sigma evolves the geometric boundary motion. It demonstrates volatility effects and positive constraints. So and the third plot will be the f and sigma correlation analysis, the scatter plot of incremental changes of delta f versus the delta sigma, and then empirically verify the correlation parameter rho. We'll calculate all increments and plot sample. So it will be something like so I will just copy paste the code of this. So it will be like something like this, and this full code will be provided in below comment section and also in description also. You can refer, for if you don't have the time to see the video, you can refer that also for easy access. So the plot 4 which I am making will be the final distributions, histograms of final f and sigma values, shows equilibrium distribution after 1 year evolution. So it will be something like this, and so there is some error. Let me check where we are doing the mistake. So let me see. Cannot unpack. Not. I think so. We have a command error here. So oh, okay. This error, when I was writing the code the first time, the same error I committed. So this error I committed again. So I forgot to write the return statement. So returning nothing. So yeah, it's here. It's something like here. Same error again. That's not good. be something like this. Return paths and sigma paths. Error is resolved, so the error is resolved. So let me see the graph. So these are the graphs which we are getting. So the main reason the graphs are coming like this, so we have to get too large, and so I think so when I have written I think so there's a error in Z2 I have defined. So the character the error, so the error was that the return statement was on the loop, so it was not outside. So I was the small error which committed, so it took some time. So the plot one here is showing the forward rate of interest, so how F evolves under SABR dynamics and demonstrate stochastic volatility effects on forward rates. And the plot 2 it shows how sigma evolves as geometric Brownian motion and demonstrate volatility effects and positive constraint. And third is plot 3, which is F sigma correlation analysis. So with scatter plot of incremental changes delta F and delta sigma, empirically verify the correlation parameter rho, calculate all increments and plot. So and the last is the final distribution. So histograms of final F and sigma values show equilibrium distribution after 1 year evolution. So that's the part. So now we're writing the code for section 4, that is the Hagan approximation. So let's give me the mathematical breakthrough of this. So let me define the function. Def SABR implied volatility, and the parameters will be f, k, t, alpha, beta, rho, and sigma naught. So is the complete Hagan approximation is something like this. This is a mathematical breakthrough that makes the SABR model practical. It converts the SABR SD system into closed form implied volatility. So the key components of it will be like Z parameters measures the deviation from at the money, and exit function handles the correlation effects, and the backbone correction accounts for the CV behavior, and time corrections for the parametric interactions. So let me define the epsilon. EDS to 1 E minus 7, and if absolute value of f minus k is less than epsilon, so the volatility base is defined as alpha divided by f the power 1 minus beta, and the correction the time correction we will now will do the time correction. So time correction will be defined something like this. The correction one will be 1 minus beta to the power 2 into alpha power 2 upon 24 into f to power 2 minus 2 into beta, and the correction 2 will be something like this, 0.25 into rho into beta into alpha upon f to the power 1 minus beta, and the correction 3 will be something like this, 2 minus 3 into rho to the power 2 divided by 24 into alpha power 2, and the total time correction is equal to 1 plus correction 1 plus correction 2 plus correction 3 into t, and we will return the volatility base into time correction. So let's write it was, so first we will, this condition was for add the money, so add the money case ref is equal to k, and now we'll be writing for non add the money cases the full Hagan formula. It will be something like this. So else fk equal to f into k log of fk into np dot log f upon k. And the z parameter, which is the heart of the approximation, is equal to alpha sigma naught into f to the power 1 minus beta by 2 into log square fk. And if the absolute value of z is less than epsilon, then xz is equal to 1, else let's write the square root term. The square root term will be equal to np dot square root 1 minus 2 into rho into z plus z to the power 2, and the numerator term will be something like square root term plus z minus rho, and the denominator will be equal to 1 minus rho. And if the numerator is less than equal to 0 or the denominator is less than equal to 0, then xz will be equal to 1, else xz is equal to np dot log numerator by denominator by z. Fk power is equal to Fk into 1 minus beta 2, and the backbone correction is equal to 1 plus 1 minus beta the power 2 divided by 24 into log fk power 2, and the backbone is equal to fk underscore power into the backbone correction the volatility base is equal to sigma naught divided by backbone. So the time corrections will be for this will be so the time correction now we'll be doing, that will be like term 1 be equal to 1 minus beta to the power 2 into sigma naught to the power 2 by 24. And into 1 minus to power minus beta, and the term 2 will become something like this: 0.25 into rho into beta into sigma not into alpha divided by fk power 1 minus beta, which will be divided by 2. And the term 3 is equal to 2 minus 3 into rho to the power 2 24, which will be into alpha into power 2. Her time correction is equal to 1 plus term 1 plus term 2 plus term 3 into t, and we will return the volatility base into xz into time correction. So this is a Hagan approximation, the closed form. So let's test this part. So I'm just copying the parameters and which I have already written in my code. So there's an error. Let me check. Correction 1, the error is here. The 2 into alpha 2 minus, yeah, the error is somewhere here, and so this is error. So let me correct this. There is this, so let me see. So now it's working. So now let's start with the next part, which will be the section 5th, basically the option pricing with the SABR model. So let me first define the function. It will be something like def SABR option price. Parameters will be f, it will be k, it will be t, it will be alpha, beta, and rho, sigma naught, and the option type is equal to call. So we'll be pricing the options using the SABR implied volatility plus Black-Scholes. So the method will be something like this. So we'll get the SABR implied volatility is equal to sigma, and the function will be there, and we'll use Black-Scholes for equal to price. So let me first do that. So we say volatility is equal to, we already defined the function. Functions will be something like, yeah, so we will define the function here. We will directly use this function. So the volatility will be equal to this, and let's write the if conditions. If the volatility is less than or equal to 0, or the time of maturity is less than equal to 0, we will return the max of f minus k 0 if option type is equal to call, else max k minus f 0. The d1 will be equal to np dot log fk plus 0.5 into volatility to the power 2 into t, and the volatility into np dot square root t, and the d2 will be equal to d1 minus volatility into np dot square root t. And if the option type is equal to call, so we return f into norm dot cdf d1 minus k into norm dot cdf d2, and else we will return we will return something like this. We will return k into norm dot cdf minus t2 minus f into norm dot cdf minus d1, and let's test this. So I'm directly copy pasting the part which is easy or which directly written. So name k is not defined. Oh, I have written in the small alphabet. So here, yeah. So yeah, the function is also working. So let's now write the main part, the calibration engine. So let me define the function name. I'll define the class SABR calibrator. So we'll calibrate a set of parameters to market data. We'll solve the inverse problem, market volatility, and then 7 parameters. So let me first init and self dot best parameters is equal to none, and self dot calibration error to float infinity, and then I will define def objective function self mass array. We'll define the market data. So the objective is minimize weighted sum of squared errors. So alpha beta rho is equal to parameters array. So the parameters bound check, first let's do the bound check. So if alpha is less than equal to 0, or beta is less than equal to 0, less than 0, or beta is greater than 1, or the absolute value of rho is greater than equal to 1, so we will return 1000. And if the total error is equal to 0 and the total weight is equal to 0 for row in market data dot iter rows try model volatility is equal to implied volatility the row is equal to forward and the row strike then row maturity alpha beta row and then will be sigma naught let's write now the market volatility is equal to row market volatility the weight is equal to row weight and the error is equal to model volatility minus the market volatility to power 2. Her total error will become something like plus will add to weight into error and total weight plus minus is equal to weight. So except we return 1000 and then we will return total error upon total weight if total weight is greater than 0 else it will be 1000. So now let's build another function for calibrate self market data. We run optimization to find the best parameters, so it will be the bounds will be set something like this, so 0.01 so 2.0 0.01 0.99 and minus 0.99 to 0.99 and the initial guess, let's say the initial guess x naught is equal to 0.2 and 0.5 and minus of 0.3. So the result will be equal to minimize self dot objective function and then will the x naught, then it will be args is equal to market data be bounds will be equal to bounds and the method will be equal to L B F G S B. So if the result dot success the self dot calibration error is equal to result dot function, then it will return true, or else it will return false. So let me check if there is an error. So in well octal there is an error here. Let me check. Alpha less than equal to, or if this was an error, yeah, this is an error. So let's move to step 7, that will demonstrate the shorted option superiority and the skew capture. So we'll show how the SABR dominates interest derivative and is superior for short dated op performances. So and it gives the excellent skew capture. So let me demonstrate that. So I will define a function for that also. We'll demonstrate SABR strengths and let me take f is equal to 0.03. So developing market, the normal choice. Let me take the strikes is equal to np dot in space and will be 0.025, and then let me do 0.035 and let me take this 11. So let's compare the short versus long dated options. So let's keep it the short t is equal to 0.25, which will be 3 months, and let me keep the long for equal to 5, so 5 years. So let's do that, and let's keep the short, let's store the short volatilities, and let's store the long volatilities. So it will be, so let's define. So I have already defined for k into strike, so let me copy the code which I have already written. So don't waste, I will explain what the plot means, and I will explain when the plot is made. So let me explain that portion. The time invested in that will be name correction 3 is not defined. So let me find the correction 3 we have defined above. So is an error, correction 3 I think so. I've committed error in this function, so let me move to this function. Let me check the error I have committed. So see the error one is this, the correction 3 part giving me this error. So I think so. So let me jump there. Okay, there is an error. So yeah. So as you can see, the smile width is 30% pronounced. So the skew magnitude is 4.4 asymmetry, and short versus long ratio is 1.3 wider, and this demonstrates the SABR model shorted superiority. So now we are coming to the final part. So we will develop the final SABR model, linking every function we have defined above, every class we have defined above. So let me write the class for SABR model, and let me define the initial function def init. The self is alpha 0.2 and beta is equal to 0.5, and the row to minus of 0.3, and the sigma will be equal to 0.25 equal to 0.25, and let me define the parameter. Self dot alpha will be equal to alpha, and the self dot beta is equal to beta, and the self dot rho is equal to rho the self dot sigma naught is equal to sigma naught, and the self dot is calibrated is equal to false. And as we already defined the functions up, so let me copy paste, like I have defined the function of implied volatility above, so let me just copy that part. So we have defined that everything above, and that calculates implied volatility, and we've also defined the function for option price. So let's copy that part also, and we have also defined the function for def calibrate. So we are building the calibration engine above, so let's copy everything we have defined above. So we are just choosing them here, and generate function also function we have defined up. So function it's very easy function, so just copying that part. So how it works, so let me give you the final demonstration. So I'll make the plots, so let me give the demonstration part. So we also discuss what it describes and what it has tell us. So let me run the code. So there is an error sigma, I think so the error is there. Okay, let me check it once. I think so the capitalization error, I think so that in part. Oh, okay, let me see. Sigma naught set apart. Okay, sigma let me see where the error is actually committed. So okay, I forgot to write here sigma naught be like this. So yeah, so we have the core this is a volatility surface we have built, and we have used the stochastic volatility processes, and we have used a closed form Hagan approximation implemented, and we have seen the short performance superiority have demonstrated, and we have captured the skew through correlation rho is equal to minus zero .4, and the production ready, and we have done 2,41,550 calculations, and this is industry standard, and this is the from mathematical insight to full production. So the model demonstrates the $1 trillion industrial derivative markets. So thanks for giving me your time and spending so much time on this video. And I will also be uploading the GitHub where this code will be available, so you can refer that also. So thank you.